Chapter 12, Part 6, Oxidation and Reduction. First, we're going to take a look at the synthesis of aldehydes and ketones, which is a bit of a review from Chapter 8. So you hopefully recall that when you take a primary alcohol and react it with a mild oxidant, such as PCC, you synthesize an aldehyde. A secondary alcohol plus any oxidant will give you a ketone, and an aldehyde plus a strong oxidant will give you a carboxylic acid. So, for example, if we react an aldehyde with chromic acid, which is a strong oxidant, we will see that at the aldehyde carbon, an oxidation occurs where we take the aldehyde functional group and turn it into a carboxylic acid. So the number of carbons stays the same, the location of the carbonyl carbon stays the same, but we are oxidizing the aldehyde to the carboxylic acid. In this chapter, we're introducing another type of oxidation. This is the reaction with Tollins's reagent. Now, Tollins's reagent, this is one that you can memorize. Just like these other oxidations, we're not going to go through a mechanism. The Tollins's reagent includes this silver ammonia salt along with ammonia and water. So these are the pieces that you want to memorize. And what this does is it takes an aldehyde and turns it into a carboxylate, which is the conjugate base of a carboxylic acid. Now, notably, the side products include silver metal and more ammonia, which is not special. What's cool about the Tollins's reagent is that when this reaction is performed, it's often actually used as a qualitative test to see if a compound contains an aldehyde functional group. And the way that you figure out if your compound contains this functional group is that silver metal will end up depositing on the surface of your reaction and on the surface of the test tube if you are shaking it thoroughly enough, creating a mirror effect. And this outcome can actually be permanent if it plates onto the glass. So you sometimes see this reaction performed around the holidays. You can actually do this inside a glass ornament, like a clear glass ornament, and shake up your reagents and get that silver metal to deposit on the ornament. So oxidation takes a compound and adds bonds to oxygen. Reduction does the opposite. So we're going to look at two different routes of reduction for carbonyl compounds. The first one is catalytic reduction. These are the types of conditions we've seen a lot of. This is going to be hydrogen gas plus a transition metal plus sometimes pressure. And then we're also going to introduce metal hydride reduction. This will include sodium borohydride. Let me go ahead and write out how we pronounce this. Sodium borohydride. This is a mild reducing agent. It can only reduce aldehydes and ketones. And we'll also talk about lithium aluminum hydride. Sorry, having issues with my pen. Let me just try that again. Lithium aluminum hydride, which is also sometimes shorthanded as LAH. And this is a much stronger reducing agent. This can reduce any carbonyl compound. So this will include aldehydes and ketones, but it's also going to include carboxylic acids and their derivatives, which is the topic of chapter 13 and 14. So sodium borohydride only works on aldehydes and ketones, Lithium aluminum hydride reduces pretty much anything that we would mix it with. So let's take a look at how we perform these reactions. So just like when we would do an oxidation, I would have you highlight the carbon that had either the alcohol or the aldehyde, and I would tell you to take that carbon and turn it into the new functional group. That's what's going to happen here. So we are reacting with hydrogen gas. And just like we've seen with previous reactions with alkenes, ultimately what's going to happen is a hydrogen is going to end up here and also here. So on both ends of the alkene, so, or sorry, the double bond, so across the double bond. And this is what we've seen before. So our carbon framework stays the same. Here is what was our carbonyl carbon. Now it's going to be a single bond to oxygen. We're going to have a hydrogen here from the hydrogen gas. We also have a hydrogen here from the hydrogen gas. Now, if I were to draw this more cleanly without all the extra stuff, I would see that all I'm drawing is cyclohexanol. And when you do a reduction, you should be able to kind of take this reaction the other way and say, okay, am I able to oxidize what I just drew into the starting material? And in this case, any oxidant would do that because we took a ketone and turned it into a secondary alcohol. So this, sorry about that, this alcohol would in fact turn into our particular ketone starting material with any oxidant. Now you can also use catalytic reductions to knock out several functional groups at once. So we know that these conditions can reduce alkenes as well as carbonyls. So we're going to do an oxidation in a couple places. We're going to be, reduction. We're going to be reducing our alkene. We're also reducing our carbonyl. So the number of carbons stays the same. I'm going to go ahead and keep drawing the aldehydic hydrogen just so we can keep track of that. This is my carbonyl carbon. I'm adding additional hydrogens to these carbons as part of the reduction of that alkene. Now keep in mind there were already hydrogens there, so these hydrogens were also already there. And our aldehyde is going to turn into a primary alcohol, and we are adding another hydrogen there. So if I were to draw out this product more plainly, this would simply be 1-butanol. Now, metal hydrides do something really similar, but the way that they do it is really different. With our catalytic reductions, we are doing an addition across a double bond, essentially. Here, we're actually doing a nucleophilic addition. We have hydride, which is H- with a lone pair, which is tiny and a strong base, which makes it a good nucleophile. So the hydride is actually coming from sodium borohydride, which is going to slowly release not all 4 equivalents of hydride, but a constant source of hydride. And that hydride is going to act like any other nucleophile would. And it's going to attack the carbonyl carbon, push those pi electrons up onto the oxygen. So in our mechanism, what we would see is that we form a tetrahedral intermediate, which is sp3 hybridized. Here's the hydride, the hydrogen that we just added. And then step 2 happens. This is a product after step 1. After step 2, step 2 is just a source of protons. We are going to protonate our alcohol. So this is our final product. And again, if I were to draw this more plainly, it would simply just be ethanol. So go ahead and pause and try the second one. see if you can write out the mechanism. I want to point out that these conditions were written out differently. With lithium aluminum hydride, you do have to make sure that you have a step 1, step 2 scenario, and we'll talk about that more in the next chapter. But with sodium borohydride, it's a much more mild reducing agent, and you are able to introduce the sodium borohydride at the same time as your proton source without too much interference, as long as it's not a strong acid, which methanol is not. So methanol is going to behave as our proton source in the end. So go ahead and pause and see if you can figure this out. Okay, so what you should have is that sodium borohydride is, again, a source of hydride. And hydride is a nucleophile. It's going to attack the carbonyl carbon, push those electrons up onto oxygen. So after that first step, you have an alkoxide. Here's the hydride that we just added. And then we're going to add in methanol, or it's there already. I'm going to pick up that proton. And I end up with my secondary alcohol. That hydride is still there. We just don't really have to write it. It's just a proton. It's just a hydrogen on that carbon now. And then we would also have methoxide. This is just a byproduct, though. It's not really something I need you to provide. What we're interested in is the reduction that we did to our ketone. And that's it for reduction with metal hydrides for now.